Welcome, everyone. It's my pleasure to introduce Justine, who's going to be talking about rationality of subregular W-algebras of type B. Feel free to start whenever you're ready.
Okay, thank you very much, Ro, for the invitation and for the introduction. I'm really happy to be here. And as I was saying a bit earlier, yes, I really like this seminar and watching the record. I think probably each week, so that's a good thing. So today I will talk about the rationality of subregular W algebra of type B. It's a work that I started this work during my PhD, and I studied the easiest case of this family here, so SO5, and then we tried to extend the result to a larger family of W algebra with Shigenori Nakatsuka. So this talk is presentation of joint work with Shigenori Nakatsuka, which is based in Alberta. So if I'm a bit afraid to be too fast, so don't hesitate to interrupt me if you have any question. So I think I know that people who attend this seminar are very familiar with vertex algebra in general, but let me just recall the main notion I will be interested in this talk. So we consider a VOA, a conformal vertex algebra, which is positively graded by the conformal vector. And we say that this VOA is rational if every positively graded module are completely reducible. So we have, for instance, example in our favorite families of VOA. So for instance, the simple affine vertex algebra is rational if and only if the level is a positive integer. And this corresponds to integrable representation over the affine Kac-Moody algebra. And the simple Virasoro vertex algebra is rational if its central charge satisfies this relation here. And this corresponds exactly to the minimal series representation of the Lie algebra. So in both cases here, we have a complete criterion for the rationality, and the rationality also match with another condition, finiteness condition, which is the C2 cofiniteness. So this condition is a condition which, we can consider it as a geometrical condition, which is because it's equivalent to say that the associated variety of vertex algebra is reduced to a point. And it shares some properties with the rationality, so it makes sense to look at these both properties in the same times. So for instance, a C2 cofinite vertex algebra has finitely many positively graded modules, and all the graded components are finite dimensional. And this is also the case of rational vertex algebra. And in fact, it has been conjectured by Zhu that rational vertex algebra is also C2 cofinite. So in both examples that I mentioned here, the rationality is also related to can have an interpretation at level of the Lie algebra, but it's not longer the case for W algebra, since W algebra are not directly construct from Lie algebras. So in fact, the W algebras are a large family with two parameters of vertex algebra associated with a nilpotent element in a Lie algebra and a complex parameter K called the level. And it is obtained by taking a certain Hamiltonian reduction of the affine vertex algebra. So this definition has been first stated by Fasquel and Fasquel for principal nilpotent element, and then it has been generalized to any nilpotent element by Kac-Swan and Wakimoto. So when we take, this class of vertex algebra is really large, as I said, we can recover the previous example. But as soon as we take Lie algebra with rank higher than 2, we will encounter some trouble, and the structure will be more complicated to exploit. However, we can say already some things about certain W-algebra, which are called exceptional. So an exceptional W-algebra is an algebra which consider it at a level which is said admissible. So it satisfies this property here, this arithmetical condition. And for such level, Tomoyuki Arakawa proved that the associated variety of the simple affine vertex algebra correspond exactly to the closure of some nilpotent orbit of the Lie algebra, which only depends on the denominator Q of the level K. Moreover, Tomoyuki computed the associated variety of the Hamiltonian reduction of this simple affine vertex algebra when it's non-zero, when the Hamiltonian reduction doesn't vanish, and it corresponds exactly to this intersection here. And so when we pick F to be a nilpotent element inside of the nilpotent orbit OQ, this intersection is reduced to a point, and so the affine vertex algebra are C2 cofinite, and the W algebra is also C2 cofinite. The simple quotient is also C2 cofinite. So by Zhu's conjecture, and it's natural to believe that it's rational, this family of exceptional W algebra are also rational. And this has been proved recently in all generality by Macrae. So Macrae gave a general conceptual proof for the rationality of the exceptional W algebra. But before him, a lot of people worked on some particular cases. So for instance, Tomoyuki proved first the result for regular any regular exceptional W algebra, principal W algebras. And then people were focused more on Lie algebra of type simply Lie type, like ADE, and often on the subregular case. And 2 years ago, during my PhD, I proved the rationality for the first non-simply Lie case, which is SP4 subregular. So this case can be considered as an analog in type BSC of the Bershevsky-Polyakov vertex algebra, which has been studied by Tomoyuki in DIF. And because it's not simply laced, we had to adapt his proof and his techniques. Some of his technique does not work in this case here. And also, I should mention that the rationality has been proved for a large family of W algebra, not only exceptional W algebra, but some of them appear in the context of the theorem by Thomas Krutzig and Andy Linshaw using trialities techniques. And of course, this result about exceptional W algebra is the rationality of exceptional W algebra is very important for the classification of the rationality of the rational vertex algebra, but it's still not a complete criterion because we have example of rational W algebra outside its exceptional level. So for instance, in the Deline exceptional series by Kawasetsu and by Andy's and Thomas' work, as I mentioned previously. Okay, so for the rest of the talk, I will focus on the type B and subregular case, as the title of my talks suggests. So we will start with the easiest example. So the case I studied during my PhD. We consider the subregular W algebra associated with, I'm too quick, I think, with the subregular nilpotent element in SO5. So this W algebra is strongly generated by 4 fields of conformal weights 2, 1, and 2, 2 respectively. Here, L will denote the subregular, the conformal vector, and J plus of conformal weight 1 is an Heisenberg field. And because in our case here, the conformal weights are small, and because we don't have a lot of generating fields, we can compute the OPs. So this is how the OPs look like. And because we have the OPs, we can have we can exploit them to prove the rationality. So the first stage to do that is to watch at the positively graded modules, and we can show in a more general context that any positive energy representation with a finite dimensional top component is an highest weight representation generated by this vector here, which satisfies this kind of relation. And moreover, when the W algebra is C2 cofinite, for instance, when the level is an exceptional level, then all the modules are of this form. So now we can give the precise statement of the theorem. So we fix K to be an admissible level corresponding to the subregular nilpotent orbit. So with denominator Q equal to 3 for the principal case, or 4 for the co-principal case. And so we are in a position to prove that the W algebra is rational, and we can explicitly describe the set of simple modules to be highest weight representation, highest weight representation of this form. So here we have the highest weight depends on 3 parameters, I, J, and S. And for the principal case, S is an integer between 1 and 3, and for co-principal case, it's equal to 1 or 2. So we have 3 families of simple module for the principal case and only 2 for the co-principal case. So I won't give any details of all the details of the proof, but I would like to introduce the most important tools to prove this theorem, which is the spectral flow twist with respect to the action of the Heisenberg fields. So we first introduce the Lie delta operator with respect to J0, and so it is defined like this, and it induces an action on the W algebra by twisting the action of the vectors. So in particular, it twists the action of L0 and J0 plus on this way here. And this spectral flow twist will send modules, an highest weight module to another highest weight module by with a different highest weight vector, of course. And also another important remark for the following. If we compose several times the highest weight, the spectral flow, it's the same than just applying spectral flow with respect to theta n time the J0 plus instead of. So in addition, the spectral flow will permute the different families of families of highest weight representation that we describe in the theorem of the rationality. And in particular, applying the spectral flow several times, it will give us enough constraint on the parameter I, J, and S to recover a finite set of simple of candidates for all simple modules. And also, so for instance, if we take the smallest, the easiest case, principal and co-principal case, the smaller levels, then we can describe all the simple module in this way. And here we have also the orbits with respect to the spectral flow. So in particular, we see that the spectral flow in the principal case, when we apply 3 times the spectral flow, we recover the same family, so it preserves the family. And it preserves the family when we apply it twice in the co-principal case. And multiplying this by 2, we recover the smallest period for the spectral flow. Okay, so this, I mentioned that the spectral flow, applying the spectral flow gives us candidates for our simple modules. However, we still need to prove the existence of these candidates. And again, the spectral flow will simplify the proof in our case. So indeed, it's enough to prove the existence of one family to recover all the simple modules here. So we can show that the first family of modules is come exactly from the Hamiltonian reduction of some highest weight representation with an highest weight in this set here, an admissible weights. And moreover, each representative in this set also appear in this way. So finally, we have a correspondence between this set here and all the modules of the first family, and we can reformulate the previous classification using only this family and the spectral flow twist. And so we have this classification of simple modules. Moreover, we conjecture that in fact all our modules, even when we apply all the twist modules, can be recovered as Hamiltonian reduction of certain highest weight modules. And to give more evidence for this conjecture and also to give some candidates for the highest weight, we computed the characters using again the spectral flow twist. And this gives us candidates here for each modules. Is there any questions so far? Okay, no question.
I have a question. Do you mind going back one slide?
Yes, sure.
So just to make sure I understand what you're saying. So what you're saying is that it's not just that by spectrally flowing all the things that you found, you get all the simples, but actually those will be Drinfeld-Sokolov reduction of a fine irreducible. That's what you're claiming.
Yes. That's why, okay, we conjecture this. We conjecture that all the modules can be recovered in this way. But so far, what we know is just one family of modules is appear in this way, and then we apply spectral flow. But yes, we expect that all come from the Drinfeld-Sokolov reduction.
Okay, thank you.
Okay. So now, a natural generalization of our work is to look for higher rank. So it's one possibility. I will discuss about another generalization later. But if we consider the W-algebra now with associated with subregular nilpotent element of SO2n plus 1, this W-algebra has a type, the type which appear here. So much more strong generator and much more OPs to compute. So because we can't really, it's really difficult in general to compute OPs, we needed to find a way to to replace this problem of computation by another techniques, by developing other techniques. And so to do so, we will try to look what we are familiar with. So for instance, we know that in this case here, the generator with highest weight 1 is still generating still a Heisenberg vertex subalgebra. And so we will look at this Heisenberg fields and trying to simplify the W-algebra using these simplifications. So indeed, we have a natural embedding of the Heisenberg vertex subalgebra generating by G plus inside our W-algebra, and this induces such a decomposition here. So we have here a decomposition over a coset times an Heisenberg vertex algebra. And it's really convenient. This description is really convenient because in fact the coset here will kill all the generator with weight 4, 6, and until 2 and minus 2. And so in this coset, only weight 1, 2, and n twice will survive. And this corresponds exactly what we had in the case n equal to 2. Okay, so sorry. So we can in fact use similar techniques than before, and for admissible level which are of this form, so we still have two families, principal and coprincipal. We can again give a classification for the simple module using the spectral flow twist, this time with a certain periodicity which depends on the rank n and on the level, sorry, and still with this correspondence with the set of admissible weights. So in fact, in the previous case, we were able to give the periodicity of the spectral flow twist, which guarantees a finiteness number of simple modules using an explicit computation. But here we just use those correspondence, and this correspondence gives us an upper bound for the number of simple modules. And then we prove that each modules which appear in this set here are non-isomorphic. And so it gives us the complete classification. So in addition, we can also exploit some techniques from Tomoyuki Arakawa and Jetro van Eekeren to prove that there are no non-trivial extension between these modules. And this gives us an alternative proof for the rationality of this W-algebra, which is the rationality is already known by Macrae's result. Okay, so I mentioned that we have still a periodicity of the spectral flow. So this periodicity is similar to one we had in the case n equal to 2. And because we have this periodicity, in fact, we also expect that in half the periodicity, the family of this kind of module is preserved. I mean that that if I apply Q bar times the spectral flow to my module coming from an highest weight representation, then I recover another module coming from the highest weight representation. And we conjecture the form of this highest weight, sorry, to be the symmetry by the Dynkin diagram of these two Dynkin diagrams here. So here we exchange these two roots, and here we switch each root by reverse case. Okay. In addition, this periodicity of the spectral flow gives us an isomorphism of modules over the coset here with this periodicity of lattice here. And as an application, I would like to give an application to this realization of modules to the unitarity case. So if we go back to the example of the case n equal to 2, we can see here that each the second parameter in each module is positive. Yes, it's positive. So in fact, the W algebra corresponding to this level here are positive. And the positive condition is also related, also appears as a condition for the unitary vertex algebra. So we say that VOA is unitary if it admits a positively definite invariant Hermitian form. And in particular, it means that the vertex algebra as a module over the Virasoro vertex algebra generated by the conformal vector must be positive. So it forces the conformal weights to be positive. And so any unitary vertex algebra is also positive. So in fact, in the case n equal to 2, we had four levels which satisfy the positive condition, and we can show that they are all they correspond all to unitary vertex W algebra. And three of these of the families appearing in the case n equal to 2 are generalized to higher rank. And so finally, we have this classification of unitary vertex algebra for subregular type. So proving this this theorem is not completely trivial, and we use the previous realization that I mentioned here. So in fact, we will we computed each module appearing here, and we finally get this kind of classification here. So the third case is the easiest one, and we can find an easier proof by using affine conformal embedding in the W algebra of the Heisenberg vertex algebra inside the W algebra. And for the three others, we had to use the computation of the asymptotical data done by Tomoyuki Arakawa, Jetro Van Ekeren, and Anne Moreau. And let me just mention that in the last case, sorry, we have the W algebra is order 3 simple current extension of this vertex algebra here. And the Virasoro module which appear here, both copies of the Virasoro module which appears here are invariant. Are different inequivariant module structure of modules. Okay. And moreover, the two copies of the Virasoro inside this last case lead us to conjecture that a generalization of this case exists, but probably in type C rather than type B. Do you have questions so far before I go to the last part? I'm sorry, I'm very quick. It's fine. Okay. So another natural generalization of our result is the extension to the super case. So in fact, we can consider the principal W superalgebra associated with the Lie superalgebra OSP 2/2n. And this W-algebra also have an Heisenberg vertex subalgebra, which satisfies this kind of relation, which is generated by this field J minus, which satisfies this kind of relation here, this OPs. And for L, which satisfy this relation here, it has been proved by Thomas Krutzing, Naoki Ganra, and Shigenori Nakatsuka that the subregular W algebra and the principal W superalgebra can be realized as a coset of their counterpart. And this kind of coset is called the Kazama-Suzuki coset construction. And so using this construction, we can recover almost for free all the, we can translate all the results we mentioned previously for the super case. So for instance, we have again a branching rule decomposition involving the lattice here as a module over the coset times the Heisenberg vertex algebra. And when the level K is admissible with corresponding to the subregular nilpotent orbit, it is known that if L satisfies a relation which is here, then the W superalgebra is rational. This is a direct implication. This is directly implied by Macrae's result and also the Kazama-Suzuki coset construction and the work of Thomas and Andy. And we can provide a complete classification of our simple module coming from the classification of simple module for the subregular case. So here we still use spectral flow, but this time we use the spectral flow with respect to the Heisenberg inside the super W algebra. And we get this classification of module here, where the only change is that the periodicity will depend on P and not on Q anymore.
What's a bar on top of PQ?
PQ bar is equal to Q when Q is principal and Q over 2 when Q is co-principal. Yeah.
Thank you.
Sorry, I should have recalled. And so we have a kind of symmetry between Q bar and P bar. And this symmetry also appears in the periodicity of the spectral flow for the super case. So in fact, here I recall that for the subregular case, the periodicity was 2Q bar, and here the periodicity is 2P bar. And this can be proved using just the Kazama-Suzuki coset construction. Okay, as an opening of to finish this talk, I would like to mention a conjecture we have. So now that we have classified all the simple module, it's natural to look at the fusion ring and also the fusion rules. And for by the realization of the set of irreducible module for the subregular case, we can realize the fusion ring as this tensor product here, where here the spectral flow will appear in the second terms. And we just with a big quote need to understand this set to understand the fusion ring of the W algebra. And for the moment, this is something that we don't know, and we don't know how to prove it, but we conjecture that in the principal case, this corresponds exactly to the fusion ring of this vertex algebra here. And so this is in accordance with the fact that each simple modules could come from the Greenfield Sokolov reduction of highest weight modules. Okay, but we don't have any ID for the co-principal case, and we would be very happy if someone come to us with an ID and to be able to prove this thing. But for the moment, it's still conjecture, and I will stop here. Thank you very much for your attention, and sorry to be so fast.
That was great. Thank you so much, Justine. Thank you. Let me stop the recording so that we can move on to more questions.